All right, guys, we're in our second lesson in our gas laws unit, and we're going to introduce two new laws. Remember, we had learned the last lesson about Boyle's law. Now there's two other individuals. There's Charles' law and Guy Lussoc's law. It says Medusa after lunch. Ralph Waldo Emerson says, shallow men and women believe in luck. Strong men and women believe in cause and effect. Think about that. Okay. You guys remember we talked about there's four factors that affect the gas. Remember, just think about gas in a balloon. We've got the gas is exerting a pressure. You can talk about the temperature of the gas, the amount of gas in there in terms of moles, and then the volume that gas takes up. Each factor affects another factor. But remember, if we want to see what effect one factor has on another, we want to keep all other factors constant. Remember with Boyle's law, Boyle concluded that pressure and volume are inversely proportional, right? You guys think about it. Let's say if I decrease the volume, what's the resulting change? There's an increase in pressure. And just think about as you're pressing on a balloon, you can feel the increase in pressure as those gas molecules are now confined to a smaller space, and thus they're going to more frequently collide. Inversely proportional, once again, this was from the last lesson. You don't have to recopy it. When one doubles, the other's half, and one triples, the other's cut in a third. So Boyle's law, you remember we could say pressure is proportional to the inverse of volume, and from that, what you'll find is pressure times volume, that the product is equal to a constant. I don't know if I had brought this up. Remember, if they're inversely proportional, that means if I were to double pressure, for example, what's the effect on volume? Wouldn't it half the volume? So that'd be volume over 2. Well, what do you guys see? 2 divided by 2, what happens? It cancels out. You guys see it's always equal to the same value. It's equal to a constant. And from that, we were able to derive this. Remember, I'm going real quick because we went over this last lesson. So whenever you have the pressure times volume is equal to a constant, regardless of which ones you change, it's always equal to the same value. You can say this is equal to this. This was Boyle's law. Okay, now we want to look at some other ones. This is one that Charles looked at. Charles looked at the relationship between volume and temperature. I think you guys could think about this. You guys think about if I were to change the temperature. Let's just go with this. Let's say if I was to increase the temperature, what effect do you guys think that might have? Assuming pressure and the number of moles of gas are constant, what effect would an increase in temperature have on the gas? What would you guys expect the balloon to do? What do you guys think? When you expect it to expand, you might come to that relationship. When you increase temperature, you increase volume. That is what Charles figured out. And he says the volume and temperature are what we call directly proportional. Okay? So what does directly proportional mean? You guys can write this down. This was already written in your previous lesson. When the value of one doubles, the other one doubles. When one triples, the other triples.
An increase in the temperature of a gas sample at constant pressure results in an increase in volume of the gas. The gas particles move faster at higher temperature, so they exert more force on the walls of the container. A container with a movable wall expands to maintain the internal gas pressure at the same value as the external.
Okay, so we can see as we increased it, molecules move faster, and if they're going to exert, right, if we're keeping pressure the same, the only way you're going to be able to keep pressure constant, right? You guys see how this is moving, so therefore the volume is able to expand and therefore maintain the same pressure. It can only do that if you have an increase in volume.
Temperature changes affect gases in other ways too. Liquid nitrogen is very cold at negative 195 degrees Celsius.
When a balloon is placed in liquid nitrogen, the air inside the balloon contracts.
When removed from the liquid nitrogen, the balloon will return to its original volume as the air warms and expands.
Let's look at a particle view of the gas inside this balloon.
So as the temperature is decreasing,
A decrease in temperature causes the particles in air to slow down. They are not hitting the sides of the balloon as hard.
and therefore the volume, to maintain the same pressure, the volume would decrease. So you guys, if we're going to graph data, right, and we know that volume and temperature are directly proportional, I want you guys to pause here to think, what do you think the graph of that data would look like? If volume and temperature are proportional, pause it, then try to think about it. And if you guys did this, you were correct. You'd expect it to look like this. What do you see? A low temperature corresponds with a low volume, and as the temperature increases, the volume increases.
So a decrease in temperature results in a decrease in volume.
The relationship between volume and temperature is a direct relationship. When one variable decreases, the other one does too.
Okay, so you guys, this is how we would mathematically show it. We'd say volume is proportional to temperature. Now you guys remember, when we're looking at the effect of one factor on another, you have to keep all other variables, in this case the other two variables, constant. There's another thing you need to make note of. You guys, this is only true when temperature is measured in Kelvin. You have to use the absolute temperature Kelvin scale. And just to remind you guys, if you ever had to convert whatever your Celsius temperature is, you're going to add 273 to get the corresponding Kelvin temperature. So this is only true when you're using the absolute temperature scale of Kelvin. Let me show you an example of that. So once again, you guys, we know volume and temperature are directly proportional. So now I'm going to just show you some data that was collected. And so let's say I already collected some data and I already graphed it, okay? So this is a volume and temperature data, okay? Let me see here. Okay, so now so we're going to go in reverse. We're going to take the graph and then put it back in as data. So we can see here, here, let me do it this way. All right, we typically do our dependent variable first, independent, and then our dependent, okay? So we'd see, so let's say these were some data points that we used to get our graph, right? Let me just line this up, right? Okay, so we see when temperature is 2, because we're going to do this as our first data point. Let's say the volume was 3. Notice I just left off units so we can just focus on this. So when the temperature was 2, the volume is 3, okay? And then our other data that we collected, so basically we just had, right, a sample of gas and we measured the temperature and the volume at various, we changed the temperature. For example, we were at 2 and then we measured the corresponding volume. We measured the temperature here at 4 and the corresponding volume is 4. Now I'm hoping you guys would look at this and notice that there's something that seems wrong. You remember we just said temperature and volume are directly proportional. Remember what that means? When one doubles, the other doubles. When one triples, the other triples. When one is half, the other is half. But look, is that the case here? Look, temperature here, when you guys agree, here the temperature doubled, but what do you notice? Did the volume double? If right, based on what we would have thought with direct proportionality, wouldn't the volume have gone from 3 to 6? It doesn't. So there's a problem here, but yet at the same time, I'm telling you guys, these are actual data that I really collected. So what do you guys think might be the problem here? And this is kind of a tricky one. It's kind of how I've set up the axes. So what could I do to adjust this? The reality here is, what this is showing you here, and you see they're not directly proportional because we're not using an absolute temperature scale. And we know that here, in this case, we know it's not an absolute temperature scale because look at here, 0, if this is 0 temperature, you guys remember if it's absolute, 0 temperature, you guys remember what 0 temperature means? It means all molecular motion is stopped. If all molecular motion stops, molecules aren't moving around, gas molecules aren't moving around, what should be the corresponding volume? If no molecules are moving around, remember molecules, atoms are infinitesimally small. Essentially, for all practical purposes, the volume should be 0. But you see at 0 here, it has an observable volume, which would indicate that the molecules are moving around. So what do we have to do? This might be an example of, for example, measuring temperature on the Celsius scale. And so you'd see, if you were collecting data and you were to measure temperature on the Celsius scale, where 0, for example, 0 Celsius does not correspond to absolutely no molecular motion, then you're going to see that the direct proportionality is not true. When are temperature and volume directly proportional? When temperature is measured on the Kelvin scale. So what do we have to do? Notice I'm not changing the data. Okay, the data points I'm just changing the scale. Look what we're going to do. We're going to make it such, so all I did was just shift it over. We're making it such that now we're using a absolute temperature scale, and we know that because look, 0 Kelvin or 0, and you guys remember the absolute temperature scale is Kelvin. 0 temperature here corresponds with 0 volume, indicating those gas molecules have completely stopped. Now look, so we're taking the same data. Now look at what we get. So now we'll reread this. Okay, so when temperature is 6, volume is 3. And now when temperature is 8, volume is 4. Okay? So now we want to see, is that true? Well, look what happened. As the temperature, wait, did I do that right? Oh, I'm sorry, I didn't do that right. Wait, did I do that? No, I'm sorry. Sorry guys. I messed that up. When temperature's 6, the volume's 3. So when temperature's 6, the volume is 3. And then when the temperature's 8, the volume is 4. Now this is a little harder to see. So when that went from 6 to 8, this went from 3 to 4. The question is, are those directly proportional? And here's how you would tell it. You go, is 6 to 8
Good morning, this is
the
Christian
same thing
Rose
as 3
with
to 4?
the morning announcement
And what you can
and the
do,
Pledge of Allegiance.
you know what, we got to do the Pledge of Allegiance.
Please
We gotta
rise
end this.
for the Pledge of
So
Allegiance.
once again, guys, we got to do our patriotic duty. So we'll take a brief hiatus.
Ready?
Just stick with me.
Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
So one sec, guys. We'll just listen to this and then we'll start.
I will now hand it off to Mr. Alcala for the morning announcements.
Thank you, Christian. Good morning, Spartans. This is Mr. Alcala with some announcements. First of all, I want to thank you for a successful first day of school yesterday. It was really awesome to have our students, teachers, and staff back in person at the home of champions. So some reminders. Please wear your masks at all times. Make sure you're covering your mouth and your nose. Also, whenever possible, wash your hands regularly with soap and water. If that's not available, please use hand sanitizer. Practice safe social distancing at all times. Yes, it also includes during lunch and before school. Make sure that you are practicing safe social distancing, at least 6 feet apart. That means 1 student per table or bench. We should not be sharing tables or benches with anyone, because that's not being 6 feet apart. Another thing is breakfast and lunch. Make sure that you pick up your breakfast and lunch every day. Remember, it is free for everyone. No PIN or ID is required. Just grab and go, get your bag, and have a great meal. Today our lunch menu is barbecue pulled pork sandwiches or chicken Caesar salads, fresh apples, Rice Krispie treats, water, and a choice of chocolate or regular milk. Please stop by one of the 4 parks at lunch for a delicious and nutritionally balanced meal. That's all I have for you today, Spartans. Make it a great day or not, the choice is yours.
All right, guys, thank you for your patience with that. So we want to see, in this case, is temperature and volume directly proportional? So we see as temperature increased from 6 to 8, we're seeing, with that change, is that proportional to an increase from 3 to 4 with volume? And you guys know how you can tell that these fractions are equal? You can just cross multiply. Maybe you learned that in math. 6 times 4 is 24. 8 times 3 is 24. That tells you that these are directly proportional. The whole point of that, excuse me, the whole point of that, guys, was to further confirm to you that this relationship is only true when the temperature is measured in Kelvin. Always, always, always convert to Kelvin when using gas laws. So if 2 things are directly proportional, their quotient, when you divide them, will always equal a constant. Check this out, right? If I were to double temperature, if they're directly proportional, what happens to the volume? Doesn't it double? Well, what happens? 2 divided by 2? Doesn't that cancel out? Don't you get the same value every time? So therefore, we can change this to, we can look at it at a certain trial, and then we can change, let's say, the volume or the temperature, so now we're going to get new temperature and volume. But once again, their quotient always equals the same value, if assuming you're measuring temperature in Kelvin. And so now what can we say? If V1 over T1 equals K and V2 over T2 equals K, what can we say? Can't we say V1 over T1 equals V2 over T2? Once again, I'm reminding you, temperature has to be measured in Kelvin. This is Charles' law in its most useful problem-solving form. So if we were dealing with a problem involving volume and temperature, we would want to use Charles' law. I find the defendant guilty. Well, what about the rest of the jury? Well, now that you asked, the old lady here seems a little suspicious. She looks guilty too. Anyways, guys, we're moving on. We're going to look at one last relationship here today. What about pressure and temperature? So you think about it, guys. So once again, we're just thinking about our balloon. So once again, this is what Guy Lussac examined. But you guys, I think we can kind of figure it out intuitively on our own. So if we're going to look at pressure and temperature, we want to keep the other factors constant, right? So obviously, I'm not going to change the amount of gas. Notice it's closed. The amount of gas, it doesn't change. And then the other thing I have to keep constant is the volume. So I can't allow the balloon to expand or contract. I got to keep it this. So now you guys think about it. How do you think those might be related? Well, think about it. If I were to heat it up, now once again, the volume can't change. If I were to heat it up, so if I were to increase temperature, what impact do you guys think that's going to have on pressure? I would imagine, when you guys think, as you increase temperature, aren't you going to increase the pressure as well? Because molecules are now moving faster, they're confined to the same amount of space, so they're going to be colliding with the walls of the container much more frequently with more energy, and therefore that's going to result in a greater pressure. So, you guys, I'm just going to cut to we're just going to skip things, and so we're just going to say pressure is proportional to temperature. So, right, you can call him Gay-Lou. We'll just call him Gay-Lou instead of Gay-Lou's law. Okay, and that's when we keep these other factors constant. But remember, all these relationships with temperature are only true if they're measured in Kelvin using the absolute temperature scale.
As the temperature increases, the gas particles have more kinetic energy, and they move more quickly. There are more collisions, and the pressure increases.
Okay, guys. So pressure and temperature are directly proportional. If we were to plot data of pressure versus temperature, what do you guys think a plot of that data would look like? If they're directly proportional, once again, you guys say this, you were correct. That's what you would expect.
So an increase in the temperature of the gas results in an increase in pressure.
The relationship between temperature and pressure is a direct relationship. When one variable increases, the other one does also. The relationship between temperature and pressure is a direct relationship. When one variable increases, the other one does also.
Okay, and so you guys, this is Gay-Lussac's his law in its most useful problem-solving form, right? Since they were directly proportional, we can set up this relationship. So you guys will write that down. But now, you guys, here's what we got. Check this out now, guys. Look at this. Okay, so here's kind of a summary of what we've got, right? We have Boyle's law, shows the relationship between pressure and volume. Charles' law, volume and temperature, and Gay-Lou's relationship between pressure and temperature. So now what I want to do is I want to make this easier for us. So for example, right, if you guys were to encounter a problem that had pressure and volume, you'd use Boyle's law. If you had to encounter a problem that dealt with changing volumes and temperatures, you do Charles, and then pressure and temperature, you use Gay-Lou's law. But now I want you guys to look at this, and then, so here in a little bit, I want you to pause it. How do you guys think you could combine it? Notice we have with combined gas law. So rather than memorizing 3 different laws, is there something we can do to just kind of combine them together in such a way that they maintain all of their same relationships? So you'd pause it here and try to think about what could you do, and hopefully you guys would realize this. Check this out, guys. we have here, guys, is the combined gas law. Notice we have all the same relationships. Pressure and volume are still inversely proportional. Volume and temperature are still directly proportional, and pressure and temperature are directly proportional. So you guys, the nice thing about this is you don't have to memorize all those anymore. All you have to know is the combined gas law. Someone would say, well, Mr. Willadsen, what if I encountered a problem that just involved pressure and volume? Let's say you encounter a problem and all it talks about is pressure and volume. What can you guys assume about temperature? Maybe you encounter a problem and it doesn't even mention temperature, so you're talking about a sample of gas. It doesn't mean it doesn't have a temperature. Obviously everything has a temperature, but why it might not mention the temperature, you might be able to assume that, oh, the temperature just stays constant. Well, think about it, guys. If a temperature stayed constant, so T1 is the same as T2, right? Let's say it's 150 Kelvin, 150 Kelvin. Wouldn't you guys agree if I have this divided by this and this divided by this and these are the same, can't you just cancel those out, and what do you end up with? You end up with Boyle's law. What if you encounter a problem where there's no mention of pressure, right? So you're talking about volume and temperature, and there's no mention of pressure. Obviously, the sample of gas is exerting pressure, but maybe it's not being mentioned because the pressure is kept constant. So if the pressure is kept constant, look at your combined gas law. If P1 is the same as P2, if those are the same values, those are going to cancel out. What are you left with? You're left with Charles' law. And the same thing with the Gay-Lu's law. If there's no mention of volume, obviously there's a volume, but maybe it didn't change. If V1 and V2 stay the same, what do we end up with? We end up with Gay-Lu's law. All right. So let me see if there was anything else we were going to do. I think that might be it. Just want to make sure. So we talked about the combined gas law. Oh, duh. You guys, I want to finish with a sample problem. Okay? So you guys write this down. Very, very important. Write it down. So once again, guys, in this case, now you guys, it's not as difficult. It's not like I have to be thinking about, okay, what law am I going to apply? At this point, I'm just going to use my combined gas law. Okay. So now you guys, this looks really big and looks kind of daunting, but we kind of want to break it up, okay? So it says, what volume will a sample of gas occupy at 57 degrees Celsius and 1.05 ATM if the same gas occupies a 600 milliliter container at 27 degrees Celsius and 2.10 atmosphere? You notice what I see here? I see two temperatures, I see two pressures, so I know that there's two gases here. There's two conditions here. So what I would do is I would maybe attempt to kind of see what's going on here. But you know what? Let me go the route that I would expect you guys to go. First thing, you guys, right? What all you need to do now is you're like, okay, I'm going to just use the combined gas law. So let's just go with that. So we got the combined gas law. That would be the first thing I would do. I'd write down the combined gas law. But you guys remember what I want you guys to do is I want you guys to list what you know. So let's say you have a difficulty, drawing like a picture. Let's just go with what we have right here. Notice it says, first thing you might want to link in on is what it's asking you to find. Notice it says what volume. We want to find a volume. And you guys remember by default, what we do is we usually put our question mark in the second set, just because that's going to be our new conditions, right? So I put V2, that's my question mark. I want to know what's going to be the new volume of my sample of gas. Then you got to think, okay, what pressure and temperature go with this unknown volume? So you read it, it says, what volume will a sample of gas occupy at 57 degrees Celsius and 1.05 atmosphere? Oh, this temperature and this pressure goes with my unknown volume. So that's what I would do. I'd say 57 degrees Celsius and the pressure is 1.05 ATM. Okay. All right. And then my P, and then you see, if, and so then it gives you another set of conditions. If a 600 milliliter container at 27 degrees Celsius and 2.10 atmospheres. So now we have this set of conditions. We have our, at 600, when my gas was in 600 milliliters and it was at 27 degrees Celsius and it had a pressure of 2.10 ATM. So now this is kind of how, this is what I have. So this is what I'd be thinking, okay? So I've got my first set of conditions. I have this gas, it's 2.10 ATM, and it's 27 degrees Celsius, and it's 600 milliliters big, okay? Then, what I see is I have that same gas. Obviously, I'm gonna change the container. I'm gonna change the size of the container. I don't know at this point if it's larger or smaller, but I do know that my new pressure is 1.05 ATM, and my new temperature is 57 degrees Celsius. Okay. And what do I want to know? I want to know what is this new volume. Okay. So, you guys, I'm thinking, you guys remember what I want you to do? I want you guys to kind of get, try to make a prediction. Now, I'm not asking you guys to predict what's going to be the value, but think about what's happening. Now, look at what's happening. So we have the same sample of gas. Just measure this. It was at 2.10 atmospheres. Now check it out. Now all of a sudden, it's going to be in a container where it only exerts 1.05 atmospheres. What do you guys think? What might explain why, you know, the pressure decreased? Now, you guys, this is a little tough because you have to look at other factors too. Look at what's happening to temperature. It went from 27 degrees to 57 degrees. So what happened to the temperature? The temperature rose. Now, what do you guys think? Normally, if you were to increase temperature, what do you guys expect to happen to the pressure of the gas inside a container? When you guys expect the pressure to go up as well, you remember they're directly proportional. Molecules moving faster, colliding more. Yet, with an increase in temperature, there was actually a decrease in pressure. That tells you something about your volume. What has to be happening to volume to explain how the pressure could decrease even though the temperature increased? You know what that tells you? You must be putting this in a much larger container. That same gas must be in a much larger container. That's the only explanation why, that would explain why, even though you're increasing the temperature, the pressure is decreasing, the volume must be larger. So what am I predicting when I calculate V2? I'm predicting that it's going to be larger than the original 600 milliliter container. So now when I perform the calculation, I want to see if that's the case. So, guys, I'm looking for, you guys see I'm solving for V2. You guys see it right here. So how do I get V2 by itself? Well, first of all, I have to get rid of T2. If I'm dividing by T2, I do the inverse operation, which is multiply. What I do to one side, I do to the other. And then how do I get rid of P2? If I'm multiplying by it, I do the inverse operation, which is divide. What I do to one side, I do to the other, I divide here. And so that's what V2. V2 is equal to this all over this. So that's what I'm going to do, guys. So I got T2. Oh, this is a big thing, you guys, and this is where, see, I almost forgot. You guys, I think some of you guys even remember, what do I need to do before I punch it in? You guys remember, these relationships only hold true when temperature is measured in Kelvin. So we have to convert our Celsius to Kelvin. Remember what you do, you add 273. So that's 300K. If I add 273 here, that's 330K. Okay? So now I'm finally ready to punch it in. So T2 is 330K times P1, which is 2.10 ATM, times V1, which is 600 milliliters, divided by P2, which was 1.05 ATM, divided by T1, which was 300K. Now you guys look at your units. Your unit should work out. The Kelvin divided by Kelvin cancels, ATM divided by ATM, and you guys see the only unit left is milliliters. So my answer is going to be in milliliters, which is a good thing because I am looking for V2. And when I punch that in, I get, if I do this, times this, divided by this, and then the last thing is you divide by this, you're going to get, and I already did it, 1320 milliliters. Or if you want to convert it, because that's a lot of milliliters, there's 1,000 milliliters in a liter, it's 1.32 liters. You could say either one. Either way, you guys, that is consistent with what we were expecting. Our new volume is much larger than our old one, which explains why the pressure decreases even with an increase in temperature. All right, guys, that's all I got. Till next time.